These solution methods brought to you by Captain Jack Sparrow, I believe, without his cool hair. So we're going to kind of skip the graphical methods. I'm assuming you all know how to graph lines in your calculator or in Desmos. I will show that to show the answers, and we're going to look at two substitution methods, or two analytical / algebraic methods to solve these linear systems. So these are kind of some steps you go through. Essentially what you want to do is solve one of the two equations for one of the two variables. It doesn't matter which one. You kind of want to pick the equation that has a 1 in it for a coefficient, or -1, and solve for that, because then you won't get fractions. But like, who cares about fractions, right? No big deal. So I'll just take this first equation and I'll solve it for x by adding y to both sides. So what I have here is an expression for x. I'll then take the second equation, which says 2 times x plus y equals 1, and I'll plug into it what I just found the first equation said x was supposed to be equal to. And the beauty of this is we now have a linear equation in only one variable. That's quite straightforward for solving at this point in your mathematical career. At least it should be. If it's not, that's okay. Just get practicing, folks. So I distributed the 2. I'm combining the 2y plus y. I'm getting 3y equals 1. I'm subtracting 10 from both sides. I'm getting 3y equals -9. Oh, look at that. We love integer solutions. By the way, don't think that if you get a fractional solution, you've done something wrong. Potentially you have. A lot of times mathematicians, when we hand you these problems to practice, we like to give you clean solutions. Now, recall, we do not have the solution. What we're looking for, our answer is an x comma y. We only have half the answer. So how do we find the x? Right? Is it obvious? Hopefully, you take our new expression for y and plug it into the equation that was solved for x. So we now go back to this x equals 5 plus y and perform a substitution again. That is this, and we end up that x equals a +2. Here's our answer. Let's check our solution just to ensure that we're doing this all correct. So here comes Desmos, and I'm going to type in x minus y equals 5. Is it going to handle that? What? Who said 7? There you go. There's that equation. And then 2x plus y equals 1. Here's the beauty of Desmos. It makes it a little easier to type these in. I think maybe some of the newer calculators allow you to type the equations in like this. Most of them you have to solve them for y to get them in your calculator, or at least back when I was doing it. So there's our solution that confirms we did everything correctly. That's the substitution method. Let's get back to here. We got some questions. Are these equations consistent? Yes, because they are different equations. That's why they're no. Are these equations consistent? Yes, because there is at least one solution. Check. And are they independent? Yes, because they're two different equations. So yes, two different equations. So this is a consistent independent system. Let's do another. My guess is it's not going to be consistent. Okay, so if you look at this one, I've got a 2 and a 6 as coefficients. I don't like that. I prefer to have a 1 as my coefficient and solve for that variable. So I'm going to again solve for x in the first equation by adding 3y to both sides. This then becomes my expression for x that I'm going to plug into the other equation. So -2 times whatever x is supposedly equal to plus 6y equals 5. Smash that right in there. Shazam, here it comes. And then solve away. Distribute. Plus. Oops, I messed up. I didn't mean to write a plus or minus, but there it is. Ooh, what? Look at this. -6y plus 6y, that's equal to 0. So our answer is -2 equals 5. And last I checked, that is not a true statement. Well, what does this mean? It means this is an inconsistent system, which means there are no solutions. It also means that the equations are parallel. That's exactly what they mean. So let's graph it in Desmos, and then let's do a little analysis of well, how else we could tell they're parallel. So x minus 3y equals 1, and negative 2x plus 6y equals 5. What? Oh, yeah, because I didn't put an x in there. I was going to be like, why am I wrong? Hey, there it is. Those look fairly parallel, although this doesn't show every single point. Who knows? It might intersect out there at infinity. What's another way we could show that? Recall, parallel lines have the same slope. So we could solve each of these for x. No, we want to solve them for y because that's where the slope is. So I would subtract x from both sides. I divide both sides by -3, and I'd get 1/3 x minus 1/3 looks like for this one. And then for this other equation, I would I'm adding x this time and dividing by 6. So there's my 1/3. Yep, there's my confirmation that they are parallel. We would need a different y-intercept to ensure that they are not the same line, meaning they are independent. So I need 5 divided by 6. And there's proof that they are different equations but have the same slope. So that means this is an inconsistent, independent system. Two distinct equations, so two totally different. Oh, good Lord, you can't see what I'm doing. Okay, so there I solved it. I just did it in my head. So there are two distinct equations. They have the same slope, that's the number in front of x, but they have different y-intercepts. Makes them independent. The fact that there's no solution makes it inconsistent.